Hello to you all. So we have a Brayton cycle with intercooling, regeneration and reheating. So we have two compressors. First compressor has some isentropic efficiency. Second compressor again has some isentropic efficiency and with intercooling. So we have also turbine here with some reheating, and then we have another turbine here. So we are having also a regenerator here at the outlet of the turbine second. So this turbine gives some output power, and the question says that to find efficiency of the cycle, air to fuel ratio of the combustion chamber, this part, and as well as reheater, and the mass flow rate of air. What is the mass flow rate of air? Effectiveness of the recuperator, so effectiveness of this part, and check whether energy is conserved for the steady cycle. It has to be, and the plot TS diagram. If the cycle is not using intercooler or reheater, the cycle uses intercooler and reheater as it is shown above. Everything should be done in EES. So let's see which values do we have. So the values are as follows. We have P1, we have T1. So let's say the problem statement again. We have P1, T1. We have HC. HC means the heating value of the fuel that is being used by combustion chamber as well as reheater. P ratio of the compressor 1. Pressure ratio of the compressor 2, as well as their isentropic efficiencies. And T3 minus T1, the difference in temperature between 3 and the 1, 9 and the 5, temperature difference is 5 and the 9, and 6, and temperature at 8, and the isentropic efficiency of turbine 1 and the 2, and as well as the power of the turbine 2. These are the given values. Next is to find these given values in EES. First of all, we should select the unit system in EES. Unit system, the convenient one is SI unit at Celsius, kilojoules, important, kilopascals, mass. Why do we select these units? Because they are easier and the common ones. So I select OK. Or you can enter unit system like here, unit system, SI at kilojoules, kilopascals, mass, and the Celsius. It's better because whoever opens your EES file will see the unit system here, or you can change unit system here easily. For example, instead of kilojoules, you can write joules, etc. So now let's write the given values for us. So let's see the given values. So first of all, P1. So we should say given values. So P1 is how much? 101 kilopascals. T1 is how much? 20 Celsius. HC is how much? 45 megajoules by kilogram. We should convert this one into kilojoules by kilogram. And the pressure ratio 1 is how much? 3. And eta compressor 1 is 0.82, and P ratio 2 is 3. Again, same pressure ratio as we have. Eta compressor 2 is 0.83, and the T3 minus T1 is 8 Celsius, and the T9 minus T5 is 65 Celsius, and the T6 is 1310 Celsius, and the T8 is 1300 Celsius, and the isentropic efficiency of the turbine 1 is 0.85, and isentropic efficiency of turbine 2 is 0.89, and power of turbine 2 is 500 HP, and we should convert HP into kilowatts. Let's see if it works. We have some unknowns. For one equation is missing, so instead of T3 minus T1 we can comment this one out, because we have unknowns here. So yes, everything works, and we have also this table of arrays. So let's start from one by one. So first of all, for the thermodynamic cycles, we should always have the known enthalpy values. Okay, so important thing is enthalpy. Okay, for all of the cycles you should have the enthalpy values known. So therefore our aim for this problem is to find the enthalpy values. Which enthalpy values? Yes, so first of all H1 is enthalpy. First of all, our working fluid is what? Air. Enthalpy 1, so enthalpy 1 is enthalpy air, T is T1. So this part is clear, so the enthalpy 1 has been found. Next is enthalpy at state 2 here. So to find enthalpy at state 2, we should have temperature. If there is no temperature, we should have two properties known. So one we have is pressure, P2 is same as P1, P2 by P1 is given as P ratio 1, this one is there. And one more thing here is that we can use isentropic efficiency of the compressor that will allow us to find H2. Okay, so what is isentropic efficiency of the compressor? Isentropic efficiency of the compressor is H isentropic 2 minus H1 by H2 minus H1. H isentropic 2 is enthalpy of the working fluid. So S is S isentropic 2 and P is P2. S isentropic 2 is same as S1, and we can find S1 as entropy air, again working fluid. T is T1 and P is P1. Let's see if it works. Yes, it works, and that's correct units, kilojoules by kilogram Celsius, and again the same unit for this one, kilojoules by kilogram Celsius. Okay, so this part has been solved. So again our aim is enthalpy, so this is our aim, therefore we should find enthalpy values. Enthalpy is our aim. So second part is, okay, now we have come to state third. So let's say state 1. So you have here state 2, and then here you have state 3. For state 3 we have pressure because P3 is same as P2, and for state 3 we have T3 minus T1 is 8 degrees Celsius. So we should comment this one out. Clear the comment of this one, you will have. So let's see what we have about 3. 3 we have fixed, so we have pressure as well as temperature. So we can find enthalpy at 3, which is air, again the fluid, T is T3. So enthalpy of the 3 has been found too. Now let's come to state 4. State 4 is to be found so by again isentropic efficiency of the compressor. So eta compressor 2 is H isentropic 4 minus IH3 divided by H4 minus H3. So H3 is known, this one is known, H4 is unknown, H isentropic 4 is unknown, but H isentropic 4 can be found by air, again the fluid, P is P4 and S is S isentropic 4. So P is P4, S is isentropic 4. So by using this property, we will have enthalpy at 4. P4 by P3 is P ratio 2. So what we have said it, P ratio 2. And H4, let's see what is the error. So you have error as isentropic 4. We have not defined it yet. So S isentropic 4 is same as S3. S3 is entropy of air, again working fluid. So what do we have about 3? 3 we have T is T3 and the P is P3. So if it's press it, you will have the values for 4. So again, important thing is enthalpy, and then we will need enthalpy for all of the calculations, and the enthalpy values has been found till state 4. Now you have come to state 5. For state 5, so state 5, we don't have anything except pressure. So pressure 5 is same as pressure 4 because it is heat exchanger and we are assuming it is perfect heat exchanger with no pressure drop. Therefore P5 will be same as P4, but we don't have any other property about 5. So therefore we should first of all, let's write energy balance for the combustion chamber. So energy balance for combustion chamber. So this is our combustion chamber. So we should have energy balance. We have combustion chamber and we have some inlet which is fuel. So we have one inlet which is fuel. We have another inlet which is air. So let's do that. We have one more inlet which is air, and we have one outlet which is, what is that, 6. So for 6 we assume it is air fuel mixture as air. So we have air fuel mixture, we assume this one as air, we assume is assumed as air. So therefore we will find enthalpy for air. So this part we have air as well as we have fuel. So therefore we should write energy, first law for this system. First law for this system will be HC of the fuel, air enthalpy, and this one. So let's write one by one. So first law. So first law. So enthalpy 4 into m dot air plus HC into m dot fuel is equal to, now 5, enthalpy 6, the previous one is enthalpy 5, HC into m dot fuel into m dot air plus m dot fuel. So again we assume here this enthalpy as air, and because we assume it as air, so HC is there. So what we will do, divide each term by m dot air. What you will have, if you divide by m dot air, you will have H5 plus HC by air to fuel ratio of combustion chamber. Okay, should be equal to H6 into 1 plus 1 by air to fuel ratio of combustion chamber. So where air to fuel ratio of the combustion chamber is m dot air by m dot fuel. So we will write this equation in EES. Okay, so let's write the equation in EES. So you will have H5 plus HC by a fuel ratio of combustion chamber should be equal to H6 times 1 plus 1 by a fuel ratio of combustion chamber. So this part is there. So we have one unknown, which is enthalpy at 5. We have another unknown, which is air to fuel ratio. We have another unknown, which is H at 6. So for H6, what we have, T6 is there. Okay, and T6 is there, P6 is same as P5, P5 is same as P4, therefore pressure is there. Therefore we can find H6 as enthalpy of air. So again, working fluid, P is P6, T is T6, therefore this part is okay. So what we will do, we will assume air to fuel ratio as 150. We assume it. Okay, this is assumed. Okay, if you press it, we will have H5 as 1449 kilojoules per kilogram, but this one is assumed value. At the end, we will have one excess equation. We will comment this one out, and then you will have the exact value for state 5. State 6 has been found. Now, this one was state 5 and 6. Now state 7. Sorry, state 7. Yes, state 7. Now state 7 will be found by isentropic efficiency of the turbine 1. So turbine isentropic efficiency is H6 minus H7 divided by H6 minus H isentropic 7. So isentropic 7 can be found as, so by the way, we should always try to find isentropic enthalpies, because they need one property at state 7, because the other property is same as 6. Therefore isentropic enthalpies are always a priority. So P is P7, and what about S is S isentropic 7. So S isentropic 7 is S6, and S6 is entropy of fluid. P is P6, as we have said, P6 is known, T is T6, and P6 is same as P5. And now we have another unknown here, which is P7. This one is unknown, so we can assume it again. P7, again it is assumed, sum of P7 we can assume as P7 P6 by 2. At the end, this one will be corrected again, assumed. So if you press it, so let's see, yes, we have the values for state 7. Now state 8, again we have this combustion process for 7. So let's do that again. So similar things, you will have similar things, air, again fuel mixture, and then this again the ratio. Now instead of air to fuel ratio, you will have air to fuel ratio of heating chamber, so reheating chamber, this part. So let's write the same one. So now you will have state 8. State 8 will be, so H7 plus HC by air fuel ratio of